8.7, pH and pKa. So a lot of this is going to be review, but there's some new stuff. And so if we need to figure out the pH of something, we have to look at the weak acid and its conjugate base, or the opposite, the weak base and its conjugate acid. And so it is a very, very, very common MCQ to compare pH and pKa, because you would be given the pH of the environment compared to the pKa, so you need to be able to compare the two. As a reminder, P of anything is negative log, so if you're given Ka, then you just want to make sure to put it in negative log in order to calculate that. So we have the HH equation from earlier, and so as a reminder, the one on your constant equation sheet is written for a weak acid. And so you can see here where this is again negative log of Ka, this is the conjugate base, and then this is the weak acid. And so just remember again, conjugate base, weak acid. If it is the opposite, where it's a weak base, then it'd be POH, PKB, and so on. So you just want to make sure to flip it if it's the weak base. So if we're specifically talking about weak acids and the conjugate base, we can compare again pH and pKa. So if the pH is less than pKa, then that means we have more of the weak acid forming compared to the conjugate base, because as a reminder, A- is conjugate base. The opposite is true if we have pH to be greater, and then if it's a weak base in the conjugate, then you gotta think about the conjugate acid concentration. So if pH is less than pKa, then conjugate acid has a higher concentration, versus the opposite is true for the base. So essentially, looking at pH and pKa is based off the ratios of base to acid. And so with that, because that is stuff I talked about in the previous sections, we have acid-base indicators. And so if we don't have a pH meter, so pH meter is something that can measure the pH at any point, so the titration curves, for example, visually we can see the titration and see where we are past the equivalence point based off of using an indicator. So for example, the lab we did for titrations, we had it go from pink to clear, or clear to pink, I can't remember which one, that was phenolphthalein. And so there's other indicators we can use. And so what happens with an indicator is usually the weak acid of the indicator changes color when it's becoming a base. And so, for example, IN just stands for a generic indicator. And so in this case, this indicator is red if it has an H attached to it. And then if it separates from that H, then it becomes yellow. And so that's pretty much how indicators work. It's detecting the H pluses, and then it can come off or be attached depending on which direction you're going, whether it's going from acidic to basic or the opposite, basic to acidic. And so the different indicators are based off the environment's pH. It is literally reacting technically to what amount of H pluses or H3O pluses there are in the solution. As a reminder, the indicator is changing color when you reach the equivalence point if you picked the correct indicator. And so there's different ones you can have. Usually there is a range for pH that an indicator is useful. So this is something you need to remember. Unfortunately, not on the constant equations sheet, but a good indicator is pKa of that indicator plus or minus 1. So that is the range that is acceptable. And so if, for example, you calculate pKa and you get 4, then it's going to be useful from the 3 to 5 pH range. If you know the equivalence point is going to happen from 3 to 5-ish, then you can use that indicator that has a pKa of 4. On the AP test, whether it's the MCQ or the FRQ, you want to choose the one that is closest to the pH of that equivalence point. Your options might not be exactly at the pH, which is fine. You want to pick the closest one if it is not included in the pH range. And so here are some examples of some indicators. So you can see that different ones are useful for different pHs, because you can have the pH scale down here, and then you can see the different indicators. You can also see some indicators have two. So for example, this one right here, that means that it would have two H's, so it'd be diprotic. And so you could see the different ones. The one that we happen to use was phenolphthalein for the lab right here. And so you can see it's going from 0 to pinkish at this range. But we could have used a more accurate one if we used other indicators. It won't give you a full list for like an FRQ, for example. So you would have maybe like 4 of these choices. They would give you the pKa or the Ka values, and then you calculate pKa and then do the range thing that I said you have to memorize on the previous slide. So just make sure that you can do that. Okay, so that's the gist of the new stuff. Again, it's really just looking at the Ka values of these guys, and then again calculating the pKa, and then comparing it to whatever pH you're going for. And so here is an example FRQ. And so you have a lot of this is review for the problem, so make sure you can identify this. And then you have the indicator chart right here, and then you'll be able to draw something based off reading what it says here. So again, I recommend pausing the video and then trying this out yourself. Alrighty, are we ready to go over it? I hope so. I hope you paused it and actually tried. So here we go. Alrighty, so I'm going to go through each thing because, again, we want to make sure we understand everything. So for the first one, identify the solution that was initially in the flask. So this was our table right here. And so we see the volume of titrant added. We saw that the pH was 1. So that means it was acidic. And so going back to the problem here, we had HCl and NaOH. So those were our two different things. And so the flask had to have HCl because it is acidic since it's less than 7. And so that makes sense. On the titration curve, circle the point. And so here I would circle it. Now this is a digital circle, so make sure that you make it smaller. It should not be that big. So just make sure to, while indicating it that it's obvious, it doesn't need to be huge, because if it's too huge, then College Board might not accept that as an answer. For part C, at the equivalence points, how many moles of the titrant have been added? And so we can see we have the volume right here. And so since we have the volume, we can convert it into liters, as I showed here. And then I would use the molarity given, so this 0.100, so that is this part right here. I made sure liters canceled out, and then I'm left with moles at the end, and then I can calculate moles. Now this problem can ask for grams instead of moles, so if that was the case, then you would do molar mass of sodium hydroxide, and then you would be good to go. For part D, so if we were to do this again, but this time with the indicator, we're using this chart right over here, which would be the best. And so since we're trying to get a pH of 7, we're trying to find the pH range that's the closest. And you can see methyl violet is really, really acidic. And so the equivalence point is not near that, because that would be over here. This guy who's yellow is 10 to 12. And so 10 to 12 would be over here. And so we're past equivalence point. So the best point, since the equivalence point is at 7, would be 4 to 6. This is too late. 4 to 6 is a lot closer to 7 in comparison to 10, because 6 is closer again to pH of 7 versus pH of 10 is not as close to 7. And so that's why it would be methyl red. For part E, you're sketching the curve if it was reversed. So the flask would have the sodium hydroxide instead, and so we would start off with something that's extremely basic, and then we would be adding the acid, and so the pH is going to decrease as it does in this graph. Now, because this is the same compounds where it says what if you reversed it, you want to make sure that you indicate the equivalence point, because the equivalence point is not going to change between these two. So make sure again to emphasize the parts that will definitely be the same, but you can estimate the curve because you don't know how big that curve is. But you should have that vertical line aspect that happens. Now, sometimes the curves, are slightly askew, so this might be slightly angled. So, for example, like that, they're really looking for the verticality of it. So just make sure it is vertical. And again, you labeled the equivalence point. And so that's pretty much it for the section. Like I said, it's pretty short. You're using the stuff that we reviewed in previous sections. The only difference is the pH range, and if the chart gives you Ka values instead, then you would need to calculate pKa, and then you could see the range from there. But in this FRQ, it gave you those. So just make sure that you can do that if you needed to do that. Otherwise, that's it. Bye!